Good morning, everyone. For the last topics, let's dive right away and continue with our AC power example 1. Okay, any questions about the initial procedure that we have, the initial steps that we have covered so far? The approach and the problem, anything? Okay, all right, so we left off yesterday at this step where we found the current I. Right, we applied Ohm's law, determined current I. From this current, obviously, we can find the power for the source, right? If you look back at all our equations, what do we have? Total power for any component can be given by the expression half VI asterisk, meaning we need only voltage and we need the current. The voltage source was already given to us. We already determined the current. And so we can apply this equation to find the total power being supplied by the source. So that's one option. Then for the components, we have the component value, so we can calculate the reactance X, right? If we have the reactance X, we only need either the current or the voltage, right? We don't have either the current or the voltage for the inductor or the capacitor. For the capacitor or the resistor, right? We don't have IR, we don't have IC. We have to calculate those. We don't have the voltage either. So we cannot yet apply these equations. We cannot yet apply these equations for the resistor or for the capacitor. We still need to find either the voltage or the current. For the inductor, however, the total current I is also the current flowing through the inductor. And so with the inductor L, we can calculate XL, the reactance for the inductor, and we can apply the equation I square RMS times X or times XL. Does that make sense? Right? You have a problem. There's only 4 quantities. If you wish to calculate power, whether it's a resistor or inductor or capacitor, there are only that many, so many equations. Okay. So depending on the quantities you have available to you, you can take multiple approaches. So every student, every engineer would decide which approach works best for them. Okay. So there is no right or wrong choice in this matter. You can either find the current and then find the power, or you can find the voltage and then find the power. All right, so let's see what we do next. So we have total current I. After that, we can find the voltage. If you back it up, total current I is coming from Vs going through Zeq. It is also flowing through the inductor and the parallel combination of the resistor and the capacitor, ZRC. So we apply Ohm's law, and you can find the voltage across the inductor as well as the voltage across the resistor and the capacitor combination. So here, VR is equal to VC. Your equation would simply be I times ZRC. Applying Ohm's law, V equals IZ. Calculate that. And this is the equation for voltage division. Okay. You can apply either Ohm's law, or you can skip that step and find it directly using voltage division. Again, multiple ways to solve the exact same circuit. These are 2 impedances connected in series. So voltage gets divided across the 2, depending on the values of these impedances. You can apply voltage division to find the voltages across the capacitor and the resistor directly. So the equations are all there. No matter which approach you choose, your answer should turn out to be the same. So I would say And I've listed this here. Practice using Ohm's law and see if you can obtain the same answers that I have right here. That's the voltage across the capacitor. Okay, I calculated it using voltage division principle. I would like students, and I would strongly suggest students find the same values by applying Ohm's law. Okay, let's take a pause, think over that. Let me know if you have any questions. Do the steps make sense? The approach makes sense? Okay. So now, as I was saying, we can use either the voltage or the current to find the power. And so here you can see on the left, I have used voltages, and on the right, this. I have used current. Left is voltage, right is current. PR is V square over R. The resistor power is the resistor voltage divided by the resistance. QL is inductor voltage divided by the inductor reactance. QC, reactive power for capacitor, is capacitor voltage divided by capacitor reactance. In all cases, you get the exact same values. 0.5 watts, 0.5 watts, minus 0.5 VR, minus 0.5 VR. Okay. The minus comes from the fact that the capacitor, of course, has a minus 90 degree impedance angle, minus 90 degree power angle. Okay. That's where the minus comes from. If you forget that concept and neglect the minus, your answer will not turn out correct. So capacitor phase would always, not phase, the angle is always minus 90. And so when we calculate power, we always insert a minus in there. Okay. So both approaches, same answers. Questions? Steps make sense? Okay. So you found the power for the resistor, the inductor, and the capacitor. The only component remaining is the source, which from the law of conservation of energy, it would make sense if the total energy being received by the three components has to equal the energy being supplied from the source. So you add everything up, and you should get total complex power S for the source. S would be equal to P plus JQ. P, of course, is the average power only associated with the resistor. Q is the reactive power only associated with capacitors and inductors. So you add up all of the average power, I mean all of the resistors in the circuit. This circuit is a simpler case where you only have one resistor, one inductor, and one capacitor. If you had multiple resistors, you would add up all of the powers for all of the resistors. That would give you the total power P supplied by the source. Similarly, if you had multiple inductors and multiple capacitors in there, you would add or subtract all the inductors together and all the capacitors together. That would give you the total energy being supplied by the source. Make sense? Right? So you get P plus JQ. P is 0.5. Q is QL plus QC. QC is minus 0.5. So 1 minus 0.5 gives you 0.5 VA. So it becomes 0.5 plus J 0.5 VA. Actually, worse. And an alternative way to determine or to solve the entire problem is by using the other equations. I'm going to give a subscript of S for the source. So if I was trying to find, so what I first approach is you find all the individual component powers together, then you add it all up, so you get the total power for the source. What if the other approach is a top-down approach? You find the total power from the source, convert it to rectangular coordinates, and then you can just find P and Q from the total power for the source. Make sense? Right? You find individual powers and then combine together to find total source power, or you find the total source power and then separate it out to find the individual component powers. And so that approach is outlined here. Standard equation, S, total complex power is a complex quantity. So S is P plus JQ. SS, subscript S is only for the source. So SS is PS plus JQS. And for this, we are going to go back 2 slides and use the equations listed here. These equations are also valid, right? You can use these equations also for every single component. The only thing is you need 3 quantities. You need the voltage, you need the current, and you need the phase angle. Well, the phase angle is, of course, the difference between the voltage and current. So once you have the voltage and current along with the phase angles, you can calculate the power angle theta. So we're going to use that to determine the total source power. And so here, I already have the voltage that is given to us, right? We know that our source angle is minus 90. We calculated that as the first step. Voltage angle is minus 90. Then the current angle is right here, minus 135. Again, remember that current I is going through the source. So we have theta V, and now we have theta I. So we can subtract the 2 and determine the power angle for the source. So minus 90 minus 135. Power angle is plus 45. Plus 45. Okay. You only need 2 quantities, voltage and current, and you can find the third. So now I have V, I have I. I need to find the RMS values from the magnitude divided by root 2. So the equation, standard equations, P is VRMS, IRMS times cosine theta, and then sine theta for Q. So this should be PS, QS. Magnitude of the power, the voltage source was 10. So 10 divided by root 2 gives me VRMS. IRMS is 0.1414 divided by root 2. Simply plug it into your calculators, perform the math, and you obtain the exact same values. 0.5 watt being supplied by the source and 0.5 VAR. So total power being supplied by the source is again the same value, 0.5 plus J 0.5 VA. Exactly the same as this. Right? Now, the only thing, of course, is that this does not give you the individual QL and QC. Okay. All right, let's take a pause, think over both approaches. Let me know if you have any questions. Any questions at all? All good with power? Ready for the quiz on Monday? Okay. Power triangle, similar to the impedance triangle. Power P is on the x-axis, real portion. Q is on the imaginary axis, 0.5 on the real axis and 0.5 on the imaginary axis. Then you join the two together, you get magnitude of S, and you have your power triangle. Makes sense, 45 degrees, so P and Q have to be equal. Or the other way is P and Q are equal, hence 45 degrees. And the way it works for the inductor, of course, is that the inductor goes up. It goes up 1 VAR, and then the capacitor supplies half of that power. So total power required in the system from the source is now reduced by half. The reactive power required by the system. Okay, QL goes up, and then QC supplies half of it, brings it down. Okay, if QC could also supply 1 VAR, then the source would not need to send any more reactive power. The system would be perfectly balanced, which of course never happens in real life. And the process of reducing the required reactive power is known as power factor correction. I think I brought it up here. Thought I had it here. Oh well. Power factor, cosine of theta. All right. Let's make a note right here. QC reduces total Q required from the source. Okay. Actually, designing and choosing power factor correction. Okay. So designing a system and choosing a value of C to balance out the power requirement is known as power factor correction. The point is we want to reduce the power required from the source. And again, of course, we are talking about steady state, meaning when the switch is first flipped on, the source has to send all of that power. But once all of that power is received from that point on, the system is at steady state, and we don't need the source to send any further power. So it sends it once and once only. So again, power factor is basically describing how much reactive power the system needs, and power factor correction, in simplest of terms, is the reduction in the amount required from the source. That is designing and choosing the value of the capacitor. And that is lab 8, for those of you who are taking the lab. Okay, that is power factor correction. So again, without QC, your power required would be this. But with QC, it's only this much. So it's now reduced. Make sense? Right. Okay. A third approach is using the equation that I mentioned up front at the very top. S is half VI asterisk. You have the voltage for the source. You have the current for the source, find the power, you have the magnitude and the phase angle, and you convert it into rectangular coordinates, you get the exact same answer, 0.5 plus j 0.5. Okay. 3 different approaches to determining the same quantity. So depending on the given problem statement, depending on the values that are given to you, depending on the quantities that are available to you, extract as much information as you can, and then decide which approach to take. As an engineer, you would be faced with a choice every day at work. Okay. Your company, whoever you work for, if you have your own startup, let's say, or you go to work for a corporation, small or big, they always want to take the most efficient. Most efficient always is in terms of the most benefits with the least amount of cost. The least amount of cost means least amount of time spent trying to find a solution. Okay. Any questions before I move on to example 2? Yes. Yes, I is the current going to the source, total current. The asterisk notes that is the complex conjugate. And you can have complex conjugate for any complex number. You could have a V asterisk or a I asterisk, any quantity. Is just complex conjugate, meaning it's flipped around the real axis. Plus becomes minus, minus becomes plus, whether the phase angle or the imaginary component. So real axis and flipped. Okay, example 2. This is a very interesting example. I really like this because nothing is given about the components. We have a system. Okay, we have a system. We are told it's a voltage source. The value of the voltage source is given to us. And there are 2 loads, A and B. A and B, 2 loads. Okay. We are not told whether it's an inductor or capacitor. We are not given anything else except what is noted right here. It'd be your job to look at the information that is given to you, that is presented to you, and extract as much information as you can. So if we take a look at this problem, we are asked to find the power triangles for the load A and B, the power triangles for the source, meaning all the 3 power triangles, then to determine the total complex power for the source. Total complex power, immediately your approach should be, you could either find the voltage and current for the source and then find total power that way, or you find the individual powers for all the individual components and add it all up together. That way you get the total complex power delivered from the source. Okay. It's the same approach that we took in chapters 1 and 2. That's no different. All right, let's take a look at what is given to us. Let's look at A. Specifically, look at the units. Remember, the units for all 3 quantities are different. Total complex power is VA volt ampere. Magnitude of the complex power is also VA, simply the magnitude of the total complex power. P is watts and Q is volt ampere reactive, VAR. So what is given here? The load is given in VA. So it means it's not P, it's not Q. VA simply means it's giving you the magnitude of the power. Okay, it's only giving you the magnitude of the power. It's not giving you anything else. So 10 kilo VA, 10,000 volt ampere is the magnitude of S for element A. Okay, that's the first thing. So 10 kVA refers to the apparent power or magnitude of S. Apparent power is magnitude of S. I've chosen the subscripts accordingly. For element A, subscript is A. For element B, subscript is B. For the source, subscript is S. Then we are told the power factor is 0.5 leading. Leading always means it's a capacitor or a capacitive load. Lagging always means it's an inductor or inductive load. Remember, Eli the Iceman. If current lags, then power factor is lagging. If current leads, power factor is leading. You're talking only about power factor, okay? Nothing else. So if it says power factor leading, it means it's a capacitive load. Power factor lagging means it's an inductive load. So we can infer from here that element A is a capacitor. Okay, element A is a capacitor. Let's look at element B or load B before we come back to A. For B, we are given the power as 5 kilowatts. 5 kilowatts. So it's 5 kilowatts. It's real power, right? It's real power or average power. Okay, average power. So it could be a resistor, right? It could be a resistor, but there's power factor in there. So if power factor is in there, that means it's not a resistor. Resistor would lie flat on the x-axis, 0 degrees. No difference between the phase and, it doesn't require any reactive power. So if it was 5 kilowatts with no power factor, then it would be a pure resistor. But because it has a power factor, then it is either an inductor or a capacitor. And then it states that it is lagging. And if it's lagging, it means it's a inductor. And so load B or element B is 5 kilowatts average power, and it means it's an inductive load. Okay, inductive load. So power triangles have to be drawn accordingly. For a capacitor, QC is negative, so it points straight down. For an inductor, QL is positive, so it points straight up. Plus 90 and minus 90, right? So this here be minus 90. And this here is plus 90. So we have the two power triangles. Okay, we have the two power triangles. Let's take a pause. You think on that. Let me know if you have questions. Again, as I said, this problem is a little different. You have to infer a lot of information is presented in the circuit diagram itself. This is something as an engineer that you would see over and over again in your own respective fields also. Any questions? The approach makes sense. We'll give you a few more seconds to think on that. Okay. All right, so then let's look at what we can do with this information. What do we have? For both, we have the power factor, meaning we have cosine of theta, meaning we have the power angle, right? For element A is cosine of cosine theta is 0.5. for element B is cosine theta is 0.7. So we can find the power angle for both. If we have the power angle, which equations can we use? We have our standard set of equations. If we have theta, we can possibly use this, right? Total complex power is magnitude of S with a phase angle of theta. Or we can also use these equations. In both cases, we either need the magnitude of S, meaning the apparent power, or we need voltage and current. So let's take a look at the solution. We are given magnitude of S, so we can use magnitude of S sine theta to determine the reactive power associated with A. It's a right angle triangle, right? The hypotenuse times sine of the angle gives you the reactive power. Q, P, this is magnitude of S, this is theta, trigonometric identities, right? Q is the hypotenuse times sine of the angle, P is hypotenuse times cosine of the angle. Okay, so you plug in those values, and you'd obtain average power and the reactive power for element A. Make sense? We can do the same for element B. Our factor is 0.7. Cosine of theta is 0.7. So angle is 45.57. We can again find all the quantities associated with element B by using trigonometric identities. Okay. So what I've done here is we want to find the magnitude of S. Excuse me. We want to find the magnitude of S. So we first find Q. Q, of course, can be given as tan of the power angle. And you find that, find QB. And then total S. Total S is, of course, on the hypotenuse, by Pythagoras theorem, root of P square plus Q square. Now it might seem obvious here because the steps are already laid out. But if you're trying to solve this problem from the beginning, you need to think about your approach, okay? And the way to think about that is look at all the quantities that are given to you and then how many paths you can take depending on which equation you'd like to use, okay? So again, equations are already there. You'll have, it's open book, open notes, all the quizzes, okay? Even the final exam, I might make it open notes. So you have the equations at your hands. You should know how to use those equations and determining the best approach, meaning the best equations to use to arrive at your solution. All right, any questions? Any questions at all? So the approach here is, of course, find total power for A, total power for B, and then add it all up to get the total source power. Okay, so we have multiple the load is just given to us. We're just saying that it's a capacitive and inductive load, but because they have real power, there's also a resistor present in there. But we don't really care about that. We're not given the circuit diagram, we're simply given the system as a whole. So remember, I stated a few minutes ago, if you have multiple resistors, you add everything up together. If you have multiple inductors and capacitors, you add up all the reactive power together. So you have real power for A, real power for B. That has to equal the total real power or average power supplied by the source, which comes out to be 10,000 watts. Okay, PA and PB. And then you have QA and QB. QA would be negative because it's a capacitor. Okay, when you are calculating, there may not be a minus sign, but because it is a capacitor, we subtract it when you add it up. You put a minus sign in front. Otherwise, your equations would never balance out. Okay. So you have total Q supplied by the source as minus 3.5 kilo VAR, volt ampere reactive. Units are even more important in this case because the units will tell you the quantity. Okay, in the circuit diagram, nothing is given to you except VA and watts W. So it'll be your job to recognize it and then extract the information and understand what it is telling you. The total SS is right here. This is in rectangular coordinates, and this is in polar coordinates. Okay, rectangular and polar coordinates. The total power factor for the entire system, minus 19. Okay, meaning the capacitor actually is providing a lot more energy than the inductor requires. Okay, it's going negative. Remember, QL points straight up, QC points straight down. So if QC is larger, than QL, then your angle, instead of being positive, is now going negative. The capacitor is actually delivering more power than is required. So it's the other way around. Capacitor actually absorbs more energy from the source in steady state. So the source power triangle is QS pointing straight down, negative. We have three triangles for the three components, the two loads and the source, and you found power for every component. Okay, questions? As I stated, this is a very interesting problem. I really like it because not a lot of information is just stated outright. We have to look at the information and glean and make conclusions from there.
Professor, can I ask a question?
Yes, go ahead.
Can you like explain again the difference between like the kVA and the kW units? Like what you
K is just the unit prefix, which is kilo,
right,
which is 1,000, 10 raised to 3.
Mhm.
And the units are basically from real power or average power. P is watts here. Reactive power is VAR, volt ampere reactive. And the total complex power S is VA, volt ampere. Magnitude of S, of course, because it's the same quantity, the units do not change. Magnitude of S is still VA. So magnitude of S is also known as apparent power and has units of VA. So in the problem, because A and B are not stated, are not explicitly stated as any particular components, nor is the power associated, it's not explicitly stated that P or Q or S is such and such a value. It simply tells you that it has a power associated as 10 kVA, 10,000 volt ampere. And so it is up to us as engineers to deduce or to deduct that VA indicates it's the magnitude of S. Okay, it's the magnitude of S. And then here, similarly for element B, W indicates that it is the average power P. Does that answer your question?
Yeah, thank you.
Okay. All right, anyone else? Okay, so this is the end of class today. We have 10 minutes left. Those who want to leave are free to leave. If you have any questions, you can stay here. Be happy to answer any questions from the entire quarter. Okay. Friday, I'm going to review pretty much everything. You are at the end. There's no more new topics to introduce. I will talk about dependent sources a little bit next week or maybe on Friday, but no other new topics, no other new homework. There's only one more quiz left, and that is on AC power. So for that quiz, that would be kind of a longer quiz, maybe 30, 35, probably not 40 minutes, but 35 minutes. It'll be everything. Okay. And I will not be I won't be assessing AC analysis or AC power on the final exam. It's only this quiz. That's it. So prepare well and show me your best work. Okay. All right. I'll see you all on Friday.